This is content of chapter 8, and we will be talking about statistical process control and then tie it into process capability. But before I do that, I do want to start to talk a little bit about process capability and why we need to do statistical process control. So process capability is the ability of a process to produce output that meets specifications, right? That conforms to specifications. So how well a process can produce outcomes that meet that answer to the voice of the customer is really the capability of the process. And generally, process capability studies answer several questions, such as where is the process centered, how much variability is in there, is the performance of it relative to specifications acceptable, what proportion of the output will be expected to meet specifications, and what factors contribute to variability, and what factors contribute to not being able to meet the specifications. So related to that is this whole notion of variation within the process. So these are examples of process variation using histograms. So here clearly lower and upper specification limits are shown, and so this is the tolerance, but the process itself, you can see that has this kind of variation and this kind of a shape. And in this particular case, the variation is small enough that it fits within the spec limit, so all is well here. But in the second one, you can see that the variation is pretty wide within the process, and but still it fits within the spec limits. But this is a very risky business, because if the variation exceeds the limits on any given day or shift, then we're not producing to specifications. In this one, you can see that the variation not only is wide, but it's also outside of the spec limit. So the whole point of this is that our spec limits are set, right? So we can't do anything about that. Our customer tells us that, but it's the variation within our process that we must be able to control. And unless we are able to control that variation, we cannot tell, or we cannot predict from day to day to day whether or not our process is going to be capable and meet those spec limits. And so that's why statistical process control is so important. We're not necessarily dealing with spec limits when we do SPC. We're trying to put control limits around our process, not spec limits, control limits around our processes, and see whether or not our production falls within those spec limits, within those control limits or not. So in that sense, the objective of process control is to provide a statistical signal when assignable causes of variation are present. Now, variation is inherent in every process. Natural or common causes of variation exist all the time, and special or assignable causes might appear at some point or part of the process. So SPC provides a statistical signal that helps us identify when those special causes of variation are present, and it helps us be more reactive and take action and remove those sources of variation quickly. So SPC measures the performance of a process. It does not identify a unit to be either good or bad or in and out of tolerance. It requires data collection and analysis. So it's not really helpful when total production is a small number of units. And even though I set up here that it does not really identify a unit to be good or bad or in or out of tolerance, but it does provide information on whether to reject, whether we can reject an entire lot of production. And the reason why it does that is because of the statistical calculations and information that goes into it. So let's talk about natural variations. Natural variations are also called common causes of variation. They affect virtually every production process. Everything around us, there is a natural variation, a set of variations in it. And a certain amount of natural variation is expected in any process. Outputs of production processes follow a probability distribution, and for any distribution, of course, there's a measure of central tendency and dispersion. And so if that distribution of the outputs falls within the acceptable limits, and by these acceptable limits we mean statistical control limits, statistical control limits, then we say that the process is within control or in control. Assignable variations are also called special causes of variations, and generally when they are present we need to do some modification, some adjustment to the process so that we can bring it back into statistical control. Variations that can be traced to a specific reason are generally assignable causes of variation, and those specific reasons are man or the human element, the person, man, machine, method, materials, measurements, and I also like to include environment. Environment would be, for instance, if there is a power surge or if there is too much humidity or too much illumination or whatever that is causing some kind of causing too much variation to be present. The objective is to discover these assignable causes of variation or special causes of variation and remove them. Eliminate the bad ones and incorporate good ones, because assignable causes aren't always bad. Sometimes they could be good for the process. So how SPC works is that we measure the process and we take samples and we analyze the sample statistics following these steps. So samples, let's say, of 5 boxes of cereal are taken every hour on the hour, right? And we average the weights of the 5 boxes, and we plot them. Eventually, after enough samples are taken, we get a shape for the distribution of the mean of the weight of the boxes of cereal. Now, this process will have its own distribution, and there are different distributions. Could normal, or it could be binomial, or it could be any type of distribution. But the point is that with any distribution, there are 3 characteristics or 3 parameters that identify that distribution, and that's the central tendency or the center of the distribution, the variation in the distribution, how peaked it is or how flat it is, and then the shape of the distribution, whether it's centered or whether it's skewed to the right or skewed to the left, or any of those conditions. So when we collect these samples and these distributions form, it could be that these distributions only exhibit natural causes of variation. And if they do, then you will get a shape like this that you see over here, that time after time after time after time, the process performs consistently the same over time. And so when a process looks like that, then it's easy for us to predict what it's going to do the next day over time. It's when the process it does not behave consistently and is not in control that we run into trouble. And so over here you can see that over time these shapes are different, right? This one is centered, this one is off-center. This one is off-center because the center is over here, and this process is, this curve is not. This one the same way, but it's pulled to the left, or it's left skewed. And so you can see that over time we don't know how it might behave, and so in the future it's a big question mark as to what it's going to do. When a process is acting like this, then it's fairly certain that there are assignable causes of variation present. And if it's so, then we cannot really say much about the capability of it and whether or not it's going to meet the customer's expectations. And this is why SPC is important, so that we can identify the assignable causes, try and remove them, adjust the process so that we remove them, and then we can get back into business. So control charts are constructed from historical data. The purpose of control charts is to help distinguish between natural causes of variation and variations that are due to special causes. Here is a view graph for process control. We sort of have covered this. You can see here in these ones over, these right over here are in a state of statistical control, and you can see that the process is capable. Now it's in statistical control. Why? Because they behave the same time after time after time, and they are in statistical and they are it's capable because our production falls within or fits within the spec limits. Over here remove these. Over here we can see that the process is in control because they all behave similarly over time, but it is not capable because there are parts of it that fall outside of the control limit. And over here, this is a process that is out of control, and it is also not capable. And generally, when a process is out of control, you don't even do anything with process capability. You don't even worry about computing or performing capability studies, because you need to get a process that's out of control, get it in control, and make it stable before you even do any capability analysis on it. So there are two different types of control charts for variables and control charts for attributes. So oops, sorry, over here this this right here should be, let me see if I can get this right. There we go. Okay, so control charts for variables follow characteristics that can take on any real value. They may be in those values may be in whole or in fractional numbers, and they are always tracking continuous random variables. So there are always two types of charts that you must use in combination with each other when you are doing control charting for variable data. and that's those two charts will track center of the distribution and variation within the distribution. So you can have either X bar and R charts, or you can have an X bar and S chart, or you can have an X and MR chart. And we'll talk about each of these. So X bar chart tracks the changes in central tendency of the distribution, the center of the distribution, or the mean. R chart indicates a gain or loss of dispersion, and it's essentially it tracks variation, but it's a very simple form of control charts because it tracks the range, or the maximum minus the minimum data values. The S chart is standard deviation chart, and it's better to use that than an R chart because it's more sensitive to variation than R chart. But it's a lot more difficult for if particularly if you're doing manual calculations to compute it rather than an R chart. This day and age, pretty much anyone who does control charting uses an automated system, so it's really not that big of a deal. And then we have X and MR charts, and with an X chart we are tracking only an individual measurement. We don't have samples because of the nature of the process. We may want to only, or we may have to only use one unit. Control charts for attributes are follow or track categorical data. So anything that's defective, not defective, good, bad, yes, no, acceptable, unacceptable, those can be charted using attribute charts. Measurements are typically counting defects, and attribute charts, there are 4 of them that we can talk about, and those are P charts, which P charts report on or track percentage of defects in each sample. And when we use P charts, N, or the sample size, could be either equal over multiple samples or unequal. So this is a proportion or a percentage chart. NP chart is very similar to a P chart, except that instead of percentage, we are tracking the number of defects in each sample. The only thing with NP chart is that it can only be used when sample sizes are equal to each other. C chart and U chart are they're counting charts in the sense that we're counting the number of defects per unit. But with C charts, there's a constant number of we can only use it when there is a constant number of opportunities for defect in each sample, whereas with the U chart, the number of opportunities for defect in each sample is not constant. So U chart give us a little bit more flexibility in that way. So all this control charting and SPC is founded on sampling and central limit theorem. Regardless of the distribution of the population, the distribution of sample means drawn from the population tends to follow a normal distribution. And the distribution of the means of the sample, the distribution of the mean of the sample means is called the sampling distribution. And so central limit theorem and sampling distribution, mean and standard deviation are given with these 2 equations right here, where X bar bar is the mean of all the sample means, and that is that represents or it estimates the population mean, and sigma sub X bar is the standard deviation of the sampling distribution, and that is approximated by standard deviation divided by square root of n, where n is the sample size. So again, central limit theorem goes to the whole notion that regardless of what the population distribution is, if you were to take samples and average and compute the mean of those samples, those means will form a normal distribution. If this is the if this peaked one is, or if this flat curve is the process distribution of the means, then this peaked one is a sampling distribution of the means. So you always get a better fit, or a tighter fit, when you are working with the sampling distribution. And a sampling distribution gets less variability in it as sample sizes increase. So here we have n equal to 25 when sample size is 50, and then when sample size is 100, you can see that the peakedness rises and the base narrows, and so we get less variation in the outcomes. So what are the steps in building control charts? You collect 20 or 25 samples, often of size n equal to 4 or 5, although it could be even as little or as few as 2. Observations are the mean of the observations is computed. The range is computed, and then over multiple samples we compute the overall mean and the overall range, and we set the appropriate control limits, which usually it's a 99.73% level, which is 3 standard deviations. So then you graph the sample means and the sample ranges. You investigate points or patterns that may form to try and see if there are any assignable causes of variation. If there are, then you must remove those variations, address the causes, make sure that the process comes within control again, and then you collect additional samples, and if necessary you may have to revalidate your control limits that you had created before, but you may have to revalidate them and compute them again with new data. So the mechanics of control charting and creating control charts is not really that difficult. I think the book does a pretty good job of using demonstration problems to show you each and every type of control chart calculation. Also, the author gives you Excel templates that are for every type of control chart. So the mechanics of it is very simple. Please study those and post any questions that you may have to the discussion boards. But I want to draw your attention to 2 things that your book offers. One is a summary table of chart formulas, and one is a flow chart. So here is table 8.5. It gives you a summary of all the formulas, and then this chart is a pretty good one in terms of what type of chart to use and when and all that. So more than anything, we need to think about managerial issues about control charts, and there are actually four major management decisions. One is the management must identify processes that need SPC. Then they need to determine the appropriate charting technique, and then set clear and specific SPC policies and procedures, and finally provide adequate training and supervision for proper implementation and execution of SPC. So once the charts are formed, then you need to interpret them. So in here we have a controlled process. There are no points outside of control limits. Number of points above and below the center line is about the same. the points seem to fall randomly above and below the center line, and most points, but not all of them, are near the center line, and only a few are very close to the control limit. So this is in general a controlled process. But typical out of control patterns are any of these: point outside of control limits, sudden shifts in the process, cycles, trends, hugging the center line, hugging the control limits. And your book goes through each of these. This is a shift in the process average. You can see that all of a sudden we are performing above the mean, and so the process average has increased. And it could be that it all of a sudden goes down. It doesn't necessarily have to be up. Here we have each of these could have a special cause associated with it. So two or three points above two of the three above two standard deviation, two standard errors. So here we have two points that are above the three standard limit. Here we have four of the five that are below the standard error. And here we have 8 points on one side of the center line. This is called a run, and you could have 8 points in a row on one side or the other side of the center line, and that generally is a sign for a cause of variation. And the reason for that is because if you're looking at this is a random process, and so there's a 0.5 probability that your process is going to behave above or create a point above the center line. And so if it's, let's say all of these are above, if for that to happen, this is above and this is below, and above and below, 0.5 and 0.5, and if you do that 8 times and multiply these 0.5 probabilities, so it's really 0.5 to the power of 8, that's a very, very small probability right there. And so for that reason, we consider that to be a special cause if something like that happens. All right. The next one is cycles. You can see over here that clearly we have cycles, and that's more than likely due to a change in shift, or maybe a change due to a change in operator, or maybe mixing of production units from various machines that produce similar types of products. Here we have a trend. Clearly there is a downward trend here, or it could be upward. And here we have a lot of the points hugging the center line. That usually, most generally, is I call that creative charting by the operators. Maybe they don't know that it's okay for the points to be all over and random in shape. And then here we have too many points hugging the control limits. So these are several types of variations that could happen, that would be a tip for us that there are special causes present, and that we must intervene and correct the situation before the production process will go on. This way we are continually monitoring the process, maybe on the hour, every hour, or very frequently, and that way we don't have to wait until the end of the shift or end of the day to do some kind of a sampling to realize that, or to check quality and to realize that there are reworks or scraps to be dealt with. As the process continues, we correct for it, and that reduces the cost of quality generally and in most cases. Okay, the next video will be short and on process capability.